I'm a fourth year undergraduate student in the Department of Mechanical Engineering. Now I'm going to present my own project for a vibrational mass control course, which is an elective course of mine. So for my project, I've made a model of tuned mass damper. I made it with wooden pieces and a string and a block of wood for a pendulum, and I put a block of brick on it, so that it won't fall when I practice on. A tuned mass damper is a device that reduces mechanical vibrations in structures like this, like huge buildings or skyscrapers. A tuned mass damper is a mass string damper that's tuned to a specific structural frequency. It's a vibrating mass that moves out of phase with the force that causes the structure to vibrate. Tuned mass dampers have been used to improve the response of building structures under room excitation. If a force is equal to a structure which has a tuned mass damper on it, it oscillates in the opposite direction of the oscillation of the structure and it dampens the oscillation of it. Let me explain how I made this model. I made this model with wooden pieces. They serve as the base and the top of the tower. Using wood provides a sturdy, rigid platform and support, essential for the stability of the entire structure. The top piece also serves as the attachment to the point of the damper system, which I use as an eye hook over here. And I used long wooden strips instead of wire, which weren't available for me, and the string to dangle in the mass from, and a block of wood as my cover. A string is attached to the center of the top wooden piece using an eye hook, and a wooden block is suspended from it to act as a pendulum. The mass moves in response to the tower's motion, and through its inertia, it provides a counteracting force that helps to dampen the vibrations. Let me show you. Without the mass, it oscillates. The frequency of this structure is more than it would be when I dangle the mass on it. Now let's try it with the mass on it. You can see that the amplitude of the vibration of the structure is way less than it was earlier, and the motion of the pendulum is in the opposite direction of the vibration of the structure. Let me explain the equations that I have written over here. So this is what my structure is. The structure and the pendulum in between, and I thought of this as an equivalent to a string block system with a pendulum dangling on it. And this is the position vector of the mass of the pendulum, and this is the velocity vector of the mass of the pendulum. This is the kinetic energy and the potential energy. From the kinetic energy and the potential energy, we have translated the Lagrangian, which is T minus 2. And from the Lagrangian equation of the partial differential of the time of the partial differential of Lagrangian with respect to velocity, and then subtracted from the partial differential of the Lagrangian with respect to the position, which happens to be these two equations with respect to the angle of deflection of the pendulum and with respect to the difference in position of the pendulum. Equations can be written in the matrix form, which is over here. If this equation is to be NNS mode, we will be supposed to get the graph of the deflection versus time, deflection of the spring versus time, and the angle versus time, the angle of the pendulum versus time. I explain more about the model design. When the tower experiences vibrations from the external force or induced motion, the vibrations are transmitted through these thin wooden strips from the bottom of the structure to the top of the structure. The suspended mass tends to stay in motion due to its inertia when the tower moves. Let me show it again. Even though the structure has stopped vibrating, the pendulum is still in motion. That's because of its inertia, obviously. This out-of-sync motion between the tower and the pendulum creates a dynamic interaction. As the pendulum swings, it absorbs some of the energy from the tower's motion, reducing the amplitude and frequency of vibration. This is the damping effect. and it helps stabilize the structure quicker than the vibration but allowed to dissipate naturally. These are very useful in earthquakes or heavy winds or thunderstorms. Natural frequency tuning. The effectiveness of tuned mass damper largely depends on the ability to resonate at a frequency that matches or complements the frequency of the structure. It's meant to stabilize. In this simple model, tuning can be accomplished by adjusting the mass or the length of the string. This model is obviously not very accurate, not at all accurate, because the string is indeterminate, so is the mass of the block, and I really wish I could have got metal wires instead of the thin wooden strips, so I could show it oscillate more better. Demonstration of damping effects. This model provides a tangible way to understand how buildings and bridges use damping system to protect against wind or seismic circumstances. Observing the mass's motion in real time can elucidate concepts of resonance. So I'm completing this video. Thank you so much.